Okay, today we're going to talk about section 3.3, graphs of polynomial functions. So first up, we're going to talk about the short-run behavior of polynomial functions, starting with intercepts. Let me make sure my tablet is on. Very good. So if I want to find the horizontal intercept of a polynomial, I have to solve for the values of our input variable, which is often x, that cause our output variable to be 0. So I can use the quadratic formula to solve a quadratic pretty easily, but while there is a cubic formula and there is a quartic formula, these formulas are very, very complicated. The quadratic formula is actually pretty simple. But these other formulas I haven't even bothered to memorize because they're so out there and complicated. And not only that, but there isn't a formula for fifth degree polynomials or higher. You can actually prove that no such formula exists. So what we're going to do is limit ourselves to 3 particular cases where we can solve for the horizontal intercepts of polynomials. And these cases are 1, where the polynomial can be factored using known methods. 2, the polynomial is already factored for us. Or 3, we use technology to determine the intercepts in some way. Typically, this is going to be through graphing a lot of the time. So let's look at an example. Sorry, I had to find my mouse. Let's find the horizontal intercepts of this polynomial. So first I want to set this polynomial equal to 0. I'm solving for the inputs that give me an output of 0. And now I can attempt to factor this polynomial. So I'm going to factor an x squared out of everything, giving me x to the 4th minus 3x squared plus 2 equals 0. And now I can actually factor the inside here like a quadratic. I need 2 numbers that multiply to give me 2, that add to give me negative 3. And those numbers are negative 1, so I'm going to have x squared minus 1, and negative 2, x squared minus 2 equals 0. I can then take all 3 of these parts and set them equal to 0 individually. Because if any single one of these 3 parts is equal to 0, then this entire expression is equal to 0, because 0 times anything is 0. I get x equals 0, because if I take the square root of both sides here, the square root of 0 is 0. Here, when I add 1 to both sides, I get x squared equals 1. So when I take the square root of both sides, I get that x is plus or minus 1. And in this last one, if I add 2 to both sides, I get x squared equals 2. Then when I take the square root of both sides, I get that x is plus or minus the square root of 2. So this gives me 5 horizontal intercepts, right? 1, 2, 3, 4, 5. You couldn't see my mouse there. 1, 2, 3, because I have a plus and a minus 1. 4, 5, because I have a plus and a minus 2. I should make that look more like a plus sign. Let's look at another one. Bloop. Find the vertical and horizontal intercepts of g of t equals t minus 2 quantity squared times 2t plus 3. So my vertical intercept can be found by just finding g of 0. This is 0 minus 2 squared times 2 times 0 plus 3. And let's see, this is going to be 4 times 3, which is 12. So if I wanted to write this as a point, I would write it as the point 0, 12. For my horizontal asymptotes, I need to take this thing and set it equal to 0. If either one of these terms is equal to 0, the entire expression is equal to 0. So I take t minus 2 squared equals 0, and 2t plus 3 equals 0. Whenever I take the square root of both sides here, the square root of 0 is just 0. No need for a plus or minus because 0 doesn't have a sign attached to it. Over here, I get 2t equals negative 3. Solving for this left one, I get t equals 2. And in this right one, I get t equals negative 3 halves. Excellent. So these are my horizontal intercepts. And if I wanted to write these as points, of course, I could write them as 2, 0 and negative 3 halves 0. Now, continuing on, find the horizontal intercepts of h of t equals t cubed plus 4t squared plus t minus 6. Now, this polynomial is, so in our first two examples, in our first example here, we were given something that was factorable. We factored this. In our second example, we were given something that was already factored for us. In this case, this is not going to be easily factorable using any techniques that we know. And it's not given to us in factored form. So, what we have to do is graph this. And I've actually already gone to Desmos and graphed this for us. You have to use x's in Desmos. There may be a way to get other letters for the variables to work that I'm not sure of. So I went ahead and graphed this, and we can see that I have horizontal intercepts at t equals negative 3, t equals negative 2, and t equals 1. Let's look at the graphical behavior of intercepts. Here I have a function graphed for us. I will make this a little larger. Here you can see I have the function x plus 3 times x minus 2 quantity squared times x plus 1 quantity cubed graphed. Notice that the behavior, each of my horizontal intercepts here, is different. If we look at this far left intercept at x equals 3, or x equals negative 3, rather, notice that the graph passes directly through the horizontal intercept. The factor that gives me this intercept, x plus 3, is linear, so the behavior near that intercept is that of a line. I'm going to say the corresponding factor x plus 3 is linear. It has a power of 1. That's what we mean by linear. So the behavior near the intercept is like that of a line. We also can call this a single zero. We call this a single zero. Next up, let's look at the far right zero. Let's look at the zero x equals 2, or the horizontal intercept x equals 2. Notice here that this comes from the x minus 2 quantity squared factor. And here the graph touches the axis at the intercept, and then it changes direction. So at x equals 2, the graph, I'm going to say, bounces off the axis. Because that corresponding factor, because x minus 2 squared is quadratic, the graph behaves like a quadratic at that intercept. And because x minus 2 quantity squared is equal to x minus 2 times x minus 2, we call this a double zero. And we say this zero has multiplicity 2. We say it has multiplicity 2 because it occurs twice. And we probably know what we're going to say about this one at this point. At this last horizontal intercept, the one that's in the middle, at x equals -1, this comes from the x plus 1 quantity cubed factor of the polynomial. We see that the graph passes through the axis here, but it flattens out a little bit first. The factor x plus 1 quantity cubed is cubic. So the graph behaves like a cubic near the intercept. We call this a triple zero, or we say this zero has multiplicity 3 because it occurs 3 times. So multiplicity is the number of times that a given root occurs. So let's look at this here. if a polynomial contains a factor of the form x minus h to the p power, the behavior near the horizontal intercept is determined by the power on the factor. So if I have a power of 1, then it passes straight through like a line. If I have a power of 2, it touches the horizontal axis and bounces off. If I have a power of 3, it passes through as it did with a power of 1, but it flattens out a bit first. For higher even powers, 4, 6, 8, etc., the graph still bounces off the horizontal axis. But it will appear flatter with each increasing even power as it approaches and leaves the axis. Same deal with higher odd powers, except they behave like the cubic, right? For higher odd powers, the graph passes through the axis. But it will appear flatter with each increasing odd power as it approaches and leaves the axis. Let's look at our next topic here. Polynomial. This is on polynomial inequalities. It's on polynomial inequalities. We want to solve this polynomial inequality. The first thing that we want to do, as with all inequalities, we want to solve for where this thing is equal to 0. So currently we have x plus 3 times x plus 1 squared times x minus 4 is greater than 0. We want to solve for x plus 3 times x plus 1 squared times x minus 4 equals 0 first. This has solutions at x equals -3, -1, and +4. We use this information combined with the fact that functions can only change from positive to negative or vice versa at their zeros, because you have to pass through 0 to go from being negative to go to being positive, or to go from being positive to being negative. So This particular function can only change its sign from positive to negative or negative to positive at these zeros, -3, -1, and 4. So I'm going to divide these inputs into 4 intervals. The inputs up here, divide these into intervals. Then I'm going to choose a test value in each interval. And evaluate the function. At each test value. To determine if the function is positive or negative in that interval. So I have these intervals. I have these solutions. X equals -3, x equals -1, and x equals 4. This lets me create the intervals. Let me actually first grab this tool. Let me go ahead and grab this tool as well. And we're going to create a little table here. No. There we go. So I'm going to have my intervals over here. No. My test value in interval. F of test value. This being what I get whenever I plug that test value into the function. And is the function greater than 0 or less than 0 at that test value, and therefore in that entire interval. Whatever sign I get whenever I plug these test values into this function is going to be the sign of everything in that interval. So I'm going to have 4 intervals. Oh, wrong thing. I'm going to have I did it again. There we go. I'm going to have x is less than -3. X is between -3 and -1. X is between -1 and 4. And x is greater than 4. These numbers are the zeros that we got previously. So I have intervals between each of my zeros, and I have an interval including everything less than -3 and everything greater than +4. So I need to choose some value of x that's in this interval. So maybe for this first interval, I will choose -4 because -4 is less than -3. In the second interval, I can choose -2 because -2 is between -3 and -1. It actually doesn't matter what number you choose in this interval as long as it is in that interval. We will get the same, we'll get a different number here, but we'll get something with the same sign, which is what matters. Between -1 and 4, 0 is always nice. And a number that's greater than 4, 5 is a good one. Remember that our function is x plus 3 times x plus 1 squared times x minus 4. This is the polynomial that we're looking at. So if I plug -4 into this, if this is f of x, then f of -4 is -4 plus 3 times -4 plus 1 squared times -4 minus 4. This is -1 times -3 squared times -8. This is going to be positive 72. Now if I just continue plugging these things into this function, if I plug in -2, I'm going to get -6. If I plug in 0, I'm going to get -12. And if I plug in 5, I'm going to get 288. Now, is 72 greater than 0 or less than 0? Well, 72 is greater than 0. -6 is less than 0. -12 is less than 0. And 288 is greater than 0. Now let's go back up to see what our question was asking us again. It was asking for us to solve for all values of this polynomial that are greater than 0. So this polynomial is greater than 0 on the intervals x is less than -3 or x is greater than 4. So let me erase all of this. So I'm looking at the intervals x is less than -3 or x is greater than 4. Or in interval notation, I could write this as -∞ to -3 union 4 to infinity. Let's look at the domain of this function. So the domain of this function, let's see. Whenever I'm finding the domain of a square root, I want to make sure that whatever is underneath the radical is greater than or equal to 0. So the first thing I want to do is find where is this thing equal to 0. Well, we could use the quadratic formula, or we could see this actually factors pretty nicely. This factors to, let's see, I'm going to rewrite this as, it's always difficult for me to see the factorization at first whenever it's like this. So what I like to do is I like to actually multiply both sides by -1 here. And if I multiply both sides by -1, then I see this is the same thing as positive t squared plus 5t minus 6 equals 0. And now I can see that this factors to be what? T plus 6 times t minus 1. And this gives me t equals -6 and t equals 1 as my horizontal intercepts. So notice that this original function here, I have this negative t squared. Maybe it's blending in with my t a little bit. But you notice that this is negative. So this original quadratic here is going to be facing down like a frown. So if I'm looking for the places where this is greater than 0, that can only happen between these intercepts. This quadratic cannot be greater than 0 at these endpoints here. If it's going to be greater than 0 anywhere, it has to be between these intercepts. So the answer here is that -6 is less than or equal to t, which is less than or equal to 1. Or we could write this in interval notation as -6 to 1, like this. Next up, let's look at factored form of polynomials. If a polynomial has horizontal intercepts at x equals x sub 1, x sub 2, etc., all the way up until x sub n, then the polynomial can be written in the factored form a times x minus x sub 1 to the p sub 1 times x minus x sub 2 to the p sub 2 power times x minus x sub n to the p sub n power. It's a bit difficult to see, but that should be a p sub n at the end there. Where each of these powers, p sub I, it says p sub I is just some number, some index, on each factor can be determined by the behavior of the graph at each of these corresponding intercepts. And the stretch factor a can be determined if I'm given a value of the function other than the horizontal intercepts. This is a lot of words, but let's look at actually doing this. Let's write a formula for the polynomial function graphed here. So I have 3 horizontal intercepts. I have a horizontal intercept at x equals -3, at x equals 2, and at x equals 5. At x equals -3 and at x equals 5, the graph passes through the axis, and it passes through it kind of in a manner like a straight line. This suggests that those factors are linear, so that I have an x plus 3, this gives me the x equals -3, times an x minus 5, this gives me x equals 5. These are both, we could write to the first power, but we don't have to. Now, and you know, I'm going to write this a in front because I may have some kind of stretch factor, right? At x equals 2, the graph bounces off of the intercept. This suggests that my corresponding factor of this polynomial is probably degree 2. So this is probably quadratic. So the factor x minus 2 is probably being squared. So this is what this polynomial looks like. Now, if I want to determine the stretch factor, I have to use another point on the graph that's not one of these intercepts, or that's not one of these horizontal intercepts. And thankfully I have one right here in the form of my vertical intercept. That's totally okay to use. I have the point 0, negative 2. In other words, if I plug 0 into this, I should get negative 2 out of it. Now I know that f of 0 is negative 2, so this is a times 3 times negative 5 times negative 2 squared is 4. So this is negative 2 equals negative 60 times a. So a is positive 1 over 30. This means that this polynomial that I had graphed up here is this, but I need to replace the a with 1 over 30. So let's scroll down a little bit here. This is 1 over 30 times x plus 3 times x minus 2 squared times, you know what, we're going to write x plus 5 actually first, or x minus 5, since that's how we had it written originally, times x minus 2 quantity squared. There we go. And let's look at the last topic and examples of this section, estimating extrema. An open box top is to be constructed by cutting out squares from each corner of a 14 centimeter by 20 centimeter sheet of plastic and then folding up the sides. Find the size of the squares that should be cut out to maximize the volume enclosed by the box. So what I'm looking at here is I have a rectangle that's maybe proportioned a little bit like this. This is probably a bit off. And in fact, this is almost definitely a bit off. Let me... Oh. This is probably a bit closer to what this actually would look like. Anyway. I have this sheet of plastic that is 14 centimeters by 20 centimeters. And I want to cut out a square from each of these corners. Pretend that these are all the same size squares. I want to cut out a square from each corner. And the width of these squares will be W, right? I mean, so the sides of all of these squares is going to be W, right? It's because squares have all four sides are the same. So, let's see. Notice that after I cut out a square from each of these ends, so let's say that this is the side that was 14 centimeters, right? And let's say this side, just because of the way I drew this, let's say this side was the 20 centimeter side. So notice then that what remains here after I cut out these squares is 20 minus 2w on this side. And on this side, I have 14 minus 2w. So now, if I were to fold these sides up, then I would have a box with dimensions 14 minus 2w by 20 minus 2w by w, because w will be the height of the box. And if I wanted to find the volume of this box, I could write this as v of w is just 14 minus 2w times 20 minus 2w times w. Now, if I want to maximize my volume, really the best thing for us to do is to graph this function and locate a maximum on the graph. Of course, considering that these squares actually can't be anything larger than 7 centimeters, right? If these squares are 7 centimeters, I've actually cut out an entire side. And it also doesn't make sense to cut out negative amounts of plastic, right? I can't do that if I'm talking about cutting things. So, if I graph this thing, which I've already done, I see here that I have a maximum volume of 339.013 centimeters cubed. And this occurs when W is equal to 2.704. So this problem asked me to find the size of squares that should be cut out to maximize the volume enclosed by the box. So the size of squares that I should cut out of these corners should be 2.704 centimeters by 2.704 centimeters. And this maximizes the volume of the box. So just to clarify one more time, whenever I find this maximum, I'm just looking for a peak in this graph here, right? I'm just looking for a peak in this graph, and I have a peak right here, and Desmos actually gives us this number if we click on it. So that will be it for section 3.3. I'll try to get 3.4 and 3.5 up as soon as possible. Sorry this one was a bit late. And I hope that everyone has a great rest of their day.